just remind myself what the question actually is.
Mhm.
Okay, identify a spatial vector and its associated operator S sub n. So it's this first part that you're stuck on?
Um, yeah, because the other one is like the -2, you just right, the minus h bar and 2, you just do the. I mean, you should be able to do it using the first one, right?
Yeah, yeah. Okay, so let me just write down some stuff here. So, here's what we know. We're given that psi is equal to, what was it again? It was 1/2 and then I square root 3. 1/2 plus I square root 3 on 2
Mhm.
minus. And so we want to find like you know, we want to find a vector n hat, a real space vector for which psi is positive, right?
Yeah.
So let's like rephrase that slightly, What is n hat such that psi spin up in that direction?
Mhm.
Well, we know the expression for plus n, right? So we know that plus n is cos theta on 2 plus plus, oh God, I hopefully I get this correct. Sine theta on 2 minus. Is that correct? Let me just double check. I always get that one wrong.
Um, I have the formula sheet, I think. It's
Yep.
correct.
So it's sine, yep. So it's here. So it's cos theta on 2 plus sine theta on 2 e to the I phi. That's what we got. Okay. So basically what this question is coming down to is given well, I know what the components are, right, of psi.
Mm.
And I know that psi ought to equal some sort of plus n. So what this question is basically asking you to do is to compare these two equations and given what the components are, work out theta and phi. Because once you know theta and phi, you can
Oh,
figure out n hat from there, right? We know
yeah.
that n hat is like, oh God, now I also have to remember this one. It's going to be, I think this one's sine theta,
Yeah.
sine phi,
Yeah.
sine theta, cos phi,
And then cos
cos
theta.
theta. Yeah, because cos theta is the Z one. That one's easy.
Yeah.
I've written that down somewhere. Maybe I should. Maybe I should add that to the formula sheet. But yeah, okay. So essentially, what this question is going to be asking you to do is to compare those two equations, figure out what theta and phi must be, and then plug that back in and tell me what direction that corresponds to in the end.
Mhm.
And then from there, the remainder of the question is, I think, relatively straightforward. Yeah, the remainder of the question is pretty yeah, I'll say that parts 2 and 3 are pretty like straightforward and will have very little calculation involved. They're more conceptual in nature, I guess.
Yeah. So the minus h bar and 2 would just be the other negative. Yeah. Okay.
Yeah, well, I couldn't possibly confirm the answer to the
Yeah.
assignment.
Yeah.
That sounds about right to me.
Yeah.
Yeah, it's just reasoning out like 2 and 3,
Mm.
basically, I would say.
Yeah. I mean, I kind of thought this was gonna be it based off like just the lectures.
Yeah,
Like I was just comparing the maths to the lectures maths.
yeah, yeah.
But yeah.
A lot
Okay.
of a lot of these questions are coming down to just, that you write down all the stuff you know. Like I basically when it comes down to is I have these three objects that I know.
Mhm.
And if I compare them all and I can eventually figure out what all of these things have to be in terms of like actual numbers, right?
Yeah. Thank you.
Samita, did you have a question? You can post it in the chat if you want to.
Yeah. Can you hear me? Sorry, I don't have my earphones.
Yep, yep, I can hear you fine.
Yeah. I was a bit confused about question 3.
Sure.
I was able to write out everything in terms of the Born rule, but I'm not too sure what to do after that.
So you're stuck on part 1 still, is that correct?
Yeah. Yeah.
Okay, cool, cool, cool. So I guess, yeah. So for part question 3, we really have like this whole collection of like information, I guess. Yeah, let me write it out like that actually, you know. We have some sort of psi. And we're not given what psi is exactly, but we're kind of given what its components are, right? So for example, x is 50%, right? And I so just kind of just like stepping through this in turn, and it's not necessarily like something where you're solving equations, but you're sort of just narrowing down ultimately, you know, psi is going to be some sort of expression like a plus b minus, right?
Yeah.
And what each of these measurements are telling me is something about a and b. Not all of them are telling me what a and b are going to be exactly, but for example, when I calculate what, you know, I can calculate what this expression is in terms of a and b if I wanted to. And something about this being 50% is telling me about the values of a and b. And I would suggest that you should basically focus primarily on the x measurements and the z measurements, and you'll see that that narrows down your like scope pretty rapidly to only a handful of states potentially. And then the y measurement, I haven't given you the exact probability, but it will basically tell you out of all the states that you have narrowed it down to, what it ought to be.
Right. Okay.
Another way of thinking about this stuff is just like on the block sphere picture. This might be less obvious, so I'll just kind of say it, but if it doesn't make sense, don't worry too much about it. So on the block sphere, I have some sort of, you know, axes. So, and I basically want to like locate where this state is on the block sphere. And what each of these measurements are telling me are like what the components are along each axis. So for example, let's call this thing the x-axis, this one. Let's call this y and z. Oh, screwed up my right hand rule. So the fact that my state, wherever it lies on the sphere, is 50-50 relative to the x-axis is kind of immediately constraining me to only a restricted set of states, if that makes sense. Because what the Born rule is telling me is that wherever this state lies on the block sphere, when I try and project it down onto these two states, onto plus and minus x, it occurs with 50-50 probability. And so if you want to think about this more geometrically rather than just using the Born rules, you can think about like where things ought to be on this sphere for all of the probabilities to make sense.
Right. Yeah.
If that doesn't make sense, maybe just return to the Born rule and try and figure out what A and B must be just out of like, you know, just out of probabilities. Might helpful to be even to start with Z, right? The Z measurements are probably going to tell me a bit more information about what A and B are directly. Obviously, there might be some sort of square root factors or like plus and minuses, but you'll see that if you just start with the Zs and then narrow it down using X's and Y's, it'll quickly become like only like one state essentially. And I think you're allowed also to use question 2 as a sort of check, like a sanity check. Yeah, part 2 of this thing is like you kind of just take your state and like confirm that the measurement statistics on Y makes sense. And so whatever you figure out the state to be, you can kind of use the Born rule to check that it matches up with the experiment, this middle experiment for Y. This one here.
Right. Okay.
Does that make sense? Or do you want me to try and explain it a different way?
No, I think that makes sense. Yeah.
Okay, cool. Yeah,
Thank
it's one of
you.
those ones that maybe looks a bit like difficult. There's a lot of text, there's a lot of like info, but really you're kind of just like thinking out through the components, trying to get A and B, and you're just narrowing it down using each of these measurements. And so in quantum physics, this is like a very standard sort of thing that we do. It's called like tomography, because obviously often we can only measure in X, Y, and Z, and so we don't necessarily know psi absolutely. And so what we often do is we prepare many copies of a state psi and measure it in different bases. And all of those statistics together allow me to pinpoint exactly what psi is going to be. You know, I can't just figure out what psi is by taking a measurement in Z, because although that might tell me what the components are in Z, there might be some phase, funky stuff going on. Maybe there's an I in there, and I would need to do measurements in different directions to figure that kind of thing out.
Yep. Thank you.
Yeah, no worries. Guys have any other questions?
Not really, but I was just here for the ride.
No. You're not meant to stay here for the entire app. You don't need it. You're meant to just
Yeah.
pop in, and if you don't have any more questions, feel free to leave. No worries.
Yeah. I was hoping some other people would have questions because I don't know, when people ask question, I'm like, oh, I didn't even think of that.
Yeah. I find the ed is good for that too. You can see what other people are getting stuck on, and something
Yeah.
that helps you clarify in your head what things are a problem. So yeah, apart from that, were the other questions in the assignment making sense? I'm guessing question 1 was pretty straightforward for you guys. Like that's kind of just working through the machinery. That's a very common question you'll see in like assignments and exams. So like, yeah.
Yeah. And then question 4 was like, it was fine. And then
Okay, good.
but then yeah, it was because there was some textbook solutions that you gave that actually were kind of similar, so that helped a lot.
Yeah. It's not meant to be a tricky one. I think a lot of people in the advanced class are having trouble with it. I think maybe they're overthinking it a bit. Whereas I think, yeah, I've encouraged you guys to really like, I've kind of said before that when you see a question with a lot of writing, it's almost like you can be assured that it's easier because you just
Yeah.
get a lot of info. And so this one is totally, question 4 is like, it looks like it might be some weird Schrodinger evolution like equations, but really I just want you to think about block spheres and spins processing around magnetic fields. That's totally like how you'll get the answer to these things.
Yeah. Part 2 was like a bit harder, but
Yeah. So I did note that there was a bit of some people might have just assumed this. I forgot to clarify that the magnetic fields are kind of equal.
yeah.
It was clear in like part 3, but I forgot to clarify for part 2. You're just kind of assuming that you're at this like, essentially you're instead of pulsing around or rotating around X and then Z like in part 1, you're rotating around basically something that's 45 degrees to Z, right?
Mhm.
In principle, you could have done it from any random direction. But I think people were getting stuck in the advanced class because they were like, oh, if I don't make one of these fields big enough, I'll like never get to the state that I want.
Yeah.
And I sort of just assume that, you can make them whatever you want to get there. And
Mhm.
if it makes things easier, you can just assume that they're equal fields. And then it should be relatively straightforward. And you can use the results that we derived in class about these general magnetic fields if you want to do that.
Yeah. Sweet. Thank you.
No worries. If you have any more questions, feel free to like pop them on Ed. I'll keep an eye on stuff like in the run up to the assignment, because I assume people will probably like get more and more worried as they maybe start to actually open the assignment and look at the questions. But yeah, I'll definitely try and keep an eye out for any questions on Ed.
Yeah. Well, thank you for the semester. It was so good.
Yeah, no worries. I'll see you guys actually. There's going to be like a review week, I think, in week 13.
Oh,
And
yes.
so obviously over the next 6 weeks, I'm sure you guys will all forget quantum physics. And so I'm going to make it my job to try and give you guys some sort of practice questions, get you back into like answering sort of questions, and like just generally like revise the like major parts of the course that we'll be testing on the exam.
That's good. Thank you.
Cool.
I'm gonna miss you yelling in the mic when you get passionate. It's so good.
Cheers.
No, for
Well, I'll
real.
see you later.
See ya. Enjoy.
Thank you.
Cheers.